So this example that we're doing here, this is an introduction to what's called a Taylor series. And a Taylor series is a power series. You guys remember what a power series is? It's an infinite series that's written as a polynomial, right? You guys remember that from yesterday? So a power series is an infinite series written as a polynomial. And a Taylor series is a power series that represents a particular function. Usually we'll use these Taylor series to represent non-polynomial functions. It doesn't really make sense to use a polynomial to approximate a polynomial. So in this example here, we're gonna examine this Taylor series, which is a power series. It's going to be written as a polynomial, and we're going to try to figure out what function it represents. So the first thing I asked you to do here is to write the first 5 terms of the series and the general term. So when we plug in 0 for the first term, we're going to have x to the 0 over 0 factorial, right? And tell you what, let's just write them all out like this, and then we'll simplify them in a second. Second term, plug in 1, we get what? X to the first over 1 factorial. Plus, third term, sorry. X squared over 2 factorial. Plus x cubed over 3 factorial. Plus, that's 4, we need one more. Lauren's doing good with these. X to the 4th over 4 factorial. You guys noticing a pattern here? So all we're doing is we're plugging in each integer, each of the next counting numbers in for n. And so then the general term is just going to be this right here. This is the general term. So it's just going to be x to the n over n factorial. And again, it's an infinite series, so we're going to show that it goes on forever. All right, so this first term here, that's going to be 1 plus x to the first over 1 factorial. Remember, 1 factorial is 1 also, so that's just going to be x. And then, like I said, for the rest of them, I'm going to leave them in factorial form, so I'm going to leave them written like this. So x squared over 2 factorial plus x cubed over 3 factorial plus x to the 4th over 4 factorial. And this is an easy enough pattern. You could really go as long as you want with this, right? Wouldn't it be nice if I just asked you to do something like that for homework? You know, 100 times or something? Okay. No. The second thing I asked you to do is take the derivative of the series expansion from our result in 1. So we want to take the derivative of this. To take the derivative of a power series, what we can do is just take the derivative of each term one at a time. And this is convenient with the power series because a power series is a polynomial. And with a polynomial, we can use the power rule. So this should be fairly straightforward, I think. What is the derivative? And I'm going to write it like this just to show what we're doing here. It's okay if you didn't do this. But we're going to take the derivative of this sum. And we're going to write out we'll just do it for the terms that we have written out. So what is the derivative of 1? Okay, what is the derivative of x? What is the derivative of x squared over 2 factorial? Let's just do this. It is going to be x, but I'm going to write it like this. It's going to be 2x over 2 factorial, right? So I just took the derivative of the top, and the 2 factorial is just a constant, so I'll leave that the same for now. We'll simplify it in a second. What is the derivative of x cubed? 3x squared, so we're going to have 3x squared over 3 factorial. What is the derivative of x to the 4th? 4x cubed, and then that's going to be over 4 factorial. And then the general term, what is the derivative of x to the n? We have n times x to the n minus 1 over n factorial. Do you guys agree with that? All right, let's simplify it then. If we simplify this, we can get rid of the 0. That's going to go away. So what we have is 1 plus, what's going to happen with this 2 and this 2 factorial? They cancel each other out, and that's just going to be x. Okay, what's going to happen with this 3 and this 3 factorial? Yeah, the 3 here is going to cancel with the 3 and the 3 factorial, and we're going to be left with 2 factorial. So we're going to have plus x squared over 2 factorial. Plus, what's going to happen with this 4 and this 4 factorial? It's going to be 3 factorial, because the 4 cancels with the 4 here, and we're left with 3 times 2 times 1, which is 3 factorial. So we have x to the 3rd over 3 factorial. Now, you didn't need to do the next term, but anybody want to guess what the derivative of the next term would be? X to the 4th over 4 factorial. Wow, that's crazy. Okay, and then moving on to the general term, what's going to happen with this n and this n factorial? Yeah, so the n is going to cancel with this n here, and so the n factorial is going to turn into an n minus 1 factorial. So we have n minus 1 factorial with x to the n minus 1 here, and so on. What do you notice? So once we simplify this derivative here, and we simplify those factorials, we end up with the same series here as we had to begin with. So when we take the derivative of the series, we get the same series. Kind of fun, isn't it? All right, so then how about the next part? We want to take the integral. So I'll put the series expansion up here again. If we're going to take the integral, we can do that term by term also. What we actually want to do here is do the antiderivative. So we're going to take the antiderivative of this series expansion. Now, when we do this, what we're actually going to find is an indefinite integral. And when we take an indefinite integral, what's one thing that we always want to include with that indefinite integral? The c, right? The constant of integration. Since this is an infinite series, it's going to go on forever. We could tag it onto the end, but then we'd have to wait for a while before we can tag it on there, right? So I'm going to put that c at the very beginning, just so I make sure I get it in. So we have this constant of integration, plus, then we're going to take the integral of 1, or the antiderivative of 1. What is the antiderivative of 1? X. What's the antiderivative of x? X squared over 2. Okay, what is the antiderivative of x squared? X cubed over 3. And then we also have our 2 factorial there, right? Don't forget that. What is the antiderivative of x cubed? X to the 4th over 4. And then we also have our 3 factorial that was there. And what is the antiderivative of x to the 4th? X to the 5th over 5. And then we also have our 4 factorial there. And then moving out to our general term here, what is the antiderivative of x to the n? Over. And then we also have our n factorial there. And that is going to continue on forever. So let's simplify like we did before. If I simplify this, the c doesn't change. That's just going to be our constant of integration plus x squared over 2, which just for the purposes of this problem, I'm going to write that as 2 factorial. You guys might be able to guess why. Plus x cubed over, what is 3 times 2 factorial? 3 factorial. What is x to the 4th? I'm sorry, what is 4 times 3 factorial? 4 factorial. And we have x to the 5th over 5 times 4 factorial, which is? And so on and so forth until we get to this term here. What do you notice? What's the difference between this and this? It's almost the same, with what difference? Just this, right? That constant of integration. So it could be off by any constant, but every term after the constant term, so every term after the 1 and the c, is exactly the same as the original function. So then my last question is, what other function has the same properties? And by the same properties, I mean, what other function can we take the derivative of and get the same thing, and take the integral of and get the same thing plus or minus a constant? So Lewis says that e to the x has the same property. If we take the derivative of e to the x, what do we get? E to the x. If we take the integral of e to the x, what do we get? E to the x plus c, right? Remember, when we do an antiderivative, we need that constant of integration. So are there any other functions that if we take the derivative, we get the same thing? If we look at the graph here, the e to the x function, which I have in blue, and the power series, just the first 5 terms of the power series, which is not very much. Remember, this is an infinite series. We just wrote down the first 5. They're between -1 and 1, they're essentially the same thing. They're really close. We can see they're starting to split off here at -1. But let's pretend like we don't have access to big, powerful computers and calculators. And we wanted to know what the value of e to the -1 is, or just 1 over e. What could we do? I could plug -1 into this function and get something that I think should be pretty close, right? If I put -1 in for x here, we're going to get 1 minus 1 plus 1/2 minus 1/6 plus 1/24. Type that into your calculator. What do you get? Okay, so we get 0.375. Now I want you to type 1 divided by e in your calculator, or e to the -1.
Close.
What do you get for that? 368 what?
No, 3678779.
Okay, so we could use this to approximate e, do the same thing we just did there, and we get what? Alright, so we get 2.7083 repeating, and if you type e to the first in your calculator, 0.718, and so on, right? That's pretty close, isn't it? It's within 100th of the actual value by just using 5 terms in this power series. And we could go further, maybe add a 6th term and get even closer, and then add a 7th term and get even closer. In fact, this alternating series here, you guys know what an alternating series is? So, yeah, it's a series that alternates between positive and negative. We can figure out a bound on the error. So at this point, I know that my approximation is within 1/24th. And the next one, I know that my approximation is going to be within whatever the next term is. And as you guys might be able to imagine with the factorials in the denominator, that's going to get really big really fast. That denominator is. Which means that our approximation is going to get really good really fast.